Find the electric field at a distance z on the perpendicular bisector of a thin rod of length 2L having uniform linear charge density lambda. So we have a thin rod whose length is 2L, and from the center of the rod, if you draw a perpendicular line, then at a distance z from the center of rod, what is the value of electric field? That is the question. It is given that the rod is having a uniform linear charge density lambda, which is equal to the total charge divided by the total length of the rod. Let us proceed. Now here you see what we have is that this is the rod, and take x is equal to 0, origin of your coordinate system, at the center of the rod, and therefore the rightmost end of rod will have the coordinate x equal to L plus L, and the leftmost corner of the rod will be at coordinate x equal to minus L. Then how are we going to find out the electric field at the point P due to this rod? As we know that due to a point charge, electric field is given by the formula kq by r square. But unfortunately, this rod is not a point charge. Okay, it cannot be converted into a point charge actually. So the basic philosophy is that we will take very small pieces of the rod. Okay, we'll take small pieces of the rod, and each small piece will be considered as a point charge, and we'll calculate the electric field at the point P due to each small piece of point charge from the rod, and then we will add all of them together at the point P. Let's proceed. So look here, from the origin, let us move a distance x to the right side, and we select here a small piece of element, very small piece, as you can see. Let us say in this small piece of the rod or small element of the rod, the amount of charge contained is dq, differential amount of charge, very small amount, dq. Then let us also say that the length of this small part of the rod is dx. In the language of calculus, dx means a small increment in the value of x. So from the origin, if you take this distance as x, then a small amount of increase in the value of x is called dx. And so dx is the length of this small piece of element of the rod which contains a charge dq. Now, can we consider this as a point charge? Of course, you see it's a very small length dx, and the rod is also thin. So this height of the rod is negligible, very small, and the length dx is also very small. So this charge dq contained here can be treated as a point charge. Now using the Coulomb's law, a point charge electric field is kq by r square. So that is the basic philosophy here. So let us use this point charge only to find out the electric field at point P. So we draw a line from the charge up to the point P, and due to this small charge dq, which is considered as a point charge, at the point P electric field would be along this direction, and directed away from the positive charge along the line joining the point charge and the point P. Let us say the magnitude of this electric field is dE, differential amount of electric field, because if the charge is very small dq, then the amount of electric field will also be very small. Let us say that is dE. And you note that direction of electric field due to a point charge is always radially outwards from the point charge. That means along the line joining the point and the point charge. Now, let us say that this distance is r. Then now can we write down using Coulomb's law that the magnitude of this electric field dE can be written as 1 upon 4 pi epsilon naught this charge dq divided by the square of distance r square. Okay, fine. Now, as you know that this rod has a linear charge density lambda, and linear charge density lambda is defined as a charge per unit length. So you see this small piece of element, in this small piece of element the charge is dq and the length is dx. So charge divided by length, that means dq by dx, that is your linear charge density lambda. So by cross multiplication can we say that this dq would be lambda into dx. This we are going to substitute here. dq is lambda into dx. Achha. then what about this r square, this distance r, square of this distance? What we can do here is that using Pythagoras theorem in this triangle, because this dotted line is a perpendicular bisector, so this angle is 90 degrees, so therefore this triangle is a right triangle, and therefore this hypotenuse would be root of z square plus x square. So this r value we are going to put here. So the next step, we get 1 by 4 pi epsilon naught, charge dq becomes lambda into dx, and square of r will become, root will be gone, and we get only z square plus x square. This expression is the magnitude of this dE. Okay, good. Now what we do next is that from the origin we will go back, we'll go to the left direction, negative side, the same distance x, and we'll take one more element here, exactly symmetrical position, same amount of charge dq and same amount of length dx. So what we are doing here, that on the right hand side of the origin we have taken one small element of charge dq, same amount of charge at same distance we are taking on the left side also. We can say they both are mirror images of each other, symmetrical. Now same manner, this dq will also produce electric field at the point P. So let us draw a line connecting the point charge and the P, and then electric field would be along the line joining the charge and the point P and would be directed radially outwards. And the magnitude of that electric field would also be equal to dE, same, because same charge dq. This dE would also be given by the same expression. Both of these dE are having same magnitude because same charge dq, same distance r on both sides. Okay, even in this triangle also you apply Pythagoras theorem, you will get hypotenuse is root z square plus x square. Good. Let's proceed further. Next, what we are going to do, that we are going to create the rectangular components of this vector dE. So you see, this is the horizontal component, or we can not horizontal, we can say parallel to the rod, and this one is perpendicular to the rod. Now how can we find out their magnitudes? For that we need angle theta. Let us suppose we defined this angle is theta over here. Okay, if this angle theta, then this angle over here, this should also be equal to theta, because this vector is parallel to the rod. So between these two parallel lines, this is the transversal, so you should have same angle over here. So this is angle theta. Now as you know from vector algebra that whenever any vector is resolved into components, then the component that will make angle theta with the vector is the cosine component. So this component is dE cos theta, and the another one would be automatically dE sin theta. Same manner we can resolve this left side dE vector also into the two components along x and along y. Okay, once again let us define that this angle, should it be theta? Yes, of course it should be same as theta, because these two triangles are congruent actually, so this must be theta. And once again, by saying that this black color line is the transversal between this green color vector and the rod, both are parallel, so therefore this angle should also be equal to theta. Now once again, the component which makes angle theta with the vector is the cos component, that means dE cos theta, and another one will be the one which makes 90 minus theta angle, that is sine component, dE sin theta. Okay, so we have resolved both the vectors into the components, and we observe that this dE cos theta, both of these are equal and opposite to each other, they will cancel each other. And what about this dE sin theta components? Both are in the same direction, so they will add with each other, and we can say net electric field at the point P must be in the y-axis direction only due to all the elements. Now you see what we can say, that we have taken here two elements, mirror images of each other. So what we can do, we can take like one element you take here, another element same distance take here. Both of them will also produce electric field along the y-axis only. So if you keep on taking elements one by one, you take one element on the right side and same distance you take another element on the left side. So both of them contribution would be only in the y-axis direction. Thus, we should not bother about the horizontal components of the electric field vector. We will only add all these dE sine theta together to find out the net electric field at the point P. Therefore, we can say the net electric field at the point P must be integration of summation. Integration is summation of 2 times of dE sine theta. As you can see, both of these elements together produce electric field 2 times dE sine theta at the point P along y-axis. So net electric field should be integration or summation of 2 dE sine theta. And what would be the limits of our integration? As you can see, x equal to 0 over here, lower limit will be x equal to 0 and upper limit will be x equal to L. That means as we move from 0 to L, as we traverse half part of the rod, right side half part of the rod, and we add 2 times of dE sine theta, we'll get the net electric field over here. We may think, why I am considering only from 0 to L? What about this part? So I would say, student, that the other part is automatically being taken care of, because as you traverse the rod from 0 to L, at every distance x you will take one small element each. Whenever you take one element on the right side, at the same time you are also taking element on the left side. That is why we are getting 2 times of dE sine theta, right? That means if you just traverse from 0 to L, automatically you are also traversing from 0 to minus L. So if you do the integration only from 0 to L and 2 times of dE sine theta, you will get the net electric field at this point. Or otherwise, there is one more way of getting the same answer, that instead of taking both dE sine theta, if we consider only one element, then one element will give its electric field dE sine theta only. So only one dE sine theta, and then your limit of integration can be from minus L to plus L. That means if you are taking only one element, then of course you have to traverse the entire rod minus L to plus L. But if you are taking both of them together, that means you are taking 2 dE sine theta, then you have to traverse only half of the rod. In both cases you will get the same answer. Let us proceed. I would prefer to use this one, second expression, for the further calculations. Now we need 2 things here. What is the value of dE? That's already written here above. And what is sine theta? What is sine theta? That also we need. From this triangle we can find out sine theta. You know, sine theta is defined as opposite side by hypotenuse. So let us focus our attention into this triangle, which is now colored in green. So this angle theta, opposite side is z, and hypotenuse is this one, root of z square plus x square. So sine theta would be z upon root z square plus x square. Put this value sine theta here. So therefore the net electric field would be equal to integration. I am taking this one, minus L to plus L, and dE value you take from here, 1 upon 4 pi epsilon naught lambda x upon z square plus x square, and into sine theta, which is this, z upon root z square plus x square. Now what happens in next step is that these denominators, this and this, multiply with each other, and we'll get the whole power 3 by 2. Okay, you see in the next step what I've done here, that z square plus x square multiply with root of z square plus x square will become z square plus x square power 3 by 2. Okay, and constants to be brought out of integration. 1 upon 4 pi epsilon is a constant, lambda is a constant because the rod has a uniform charge density, and z is also constant because z is the constant distance of the point P from the rod. So keeping aside all the constant outside, we have got this integration. Now if you perform this integration, then we get our final answer. Now how do we do this integration? If you remember the standard result from a maths textbook, that is good enough. Otherwise, I will tell you on the next page how we can do this step-by-step procedure of performing this integration. Let's go. Yes, so this was our last expression we obtained, and we are supposed to find out the integration of this much part, dx upon z square plus x square power 3 by 2. So let us say I means integration. Okay, let's I is this part integration. Now let's forget about the limits for some time. Okay, let's calculate only the integration. At the end we'll put the limits. So now for such kind of integrations, what we have to do, whenever you are having something like, you know, z square plus x square, in such a case we do a substitution method, that we will put this x, the variable x, as z tan phi. Let us say x is equal to z into tan phi. I'm, you know, assuming, let us assume that there exists an angle phi in such a manner that x can be written as z tan phi. It is possible. You may think that how can we say like this? So we can we imagine a right triangle like this? Let us imagine that there exists a right triangle whose base length is z and whose altitude is x, and this base angle is phi. So can you see that in this triangle tan phi is x upon z? That same thing is here, tan phi is equal to x divided by z, correct? So this expression is coming from this imaginary triangle. It is possible. So we can imagine an angle phi for which we can write down this expression. Let's proceed. So now we want what is the value dx. Okay, first we find out what will be dx. So what we do, differentiate this expression now. Because x is given as a function of phi, so we can differentiate x with respect to phi. That means dx upon d phi. Z is a constant. Differentiation of tan phi is secant square phi. Now what we do next, cross multiply d phi on the right side. You get dx is equal to z into secant square phi d phi. This we are going to substitute here in place of dx. Acha. What about denominator now? This one. Denominator also we should find out. So as we have already taken that x is z tan phi, so we put here. So we want to find out what is the value of z square plus x square. So we will get z square will be as it is and x square means this one. So z square tan square phi. Then we can take z square common from both the terms. So we'll get in the bracket 1 plus tan square phi. And then you know students from your 10th class maths that 1 plus tan square phi is secant square phi. One of the identities z square secant square phi is the z square plus x. But it also has power 3 by 2. So let us take the power 3 by 2. So when you take the power 3 by 2, you should take the 3 by 2 power of this. That means z square secant square phi to the power 3 by 2. So when you take this power, then this 2 will cancel with these 2 and we'll get 3. That means z cube into secant cube phi. This we are going to substitute in the denominator. So let's see what happens. So our integration becomes integral dx will be this z into secant square phi d phi divide by, now this denominator we find out z cube secant cube phi right down here. Then in the next step z will cancel z cube, make it 1 by z square, and this one secant square phi will cancel secant cube phi, will get 1 upon sec phi into d phi. And then you know 1 upon sec phi is nothing but cosine phi. So in the next step we write down integral cos phi d phi, and 1 upon z square is a constant, throw it out of the integration. Now this integration is very simple. Everybody knows this answer. Answer is sin phi. Yes. So here is our simplified result of this integration, that it is 1 upon z square sin phi. Now it is time to return back into our original variables, x. So can we now write down what is the value sin phi in terms of x? For that we should look into this triangle. Look at this triangle that we have supposed in the beginning. So in this triangle, how can you find out sin phi? We should know sin phi means opposite side by hypotenuse. So this hypotenuse is root of z square plus x square. So we can write down sin phi is opposite side x upon the hypotenuse root z square plus x square. Substitute here, we will get this integration I is equal to integration I, which becomes 1 upon z square sin phi. So that becomes 1 upon z square this sin phi. Good. Finally, we are now returning back here. We are going to substitute this value here in our E net. Okay, but before that we should not forget that in this integration we also had limits minus L to plus L. So first of all let us evaluate the limits minus L to plus L. So first we put plus L into this expression and then minus subtract, then put the lower limit. So 1 by z square, first you put x equal to plus L everywhere where you have x. So L upon root z square plus L square, then minus, then you put minus L into this expression, you will get minus L upon root z square plus L square. Square of the negative term will be obviously positive here, okay, plus L square. Now what is, does it become 0? No, of course not. You see, minus become plus. So we are getting actually 2 times of L in the numerator, 2 times of L upon root z square plus L square, and this z square comes here. Okay, so finally we have evaluated with the limits in this integral fully. So just put it in front of this constant. So net electric field would be, in the next page we are going, and we are going to write down here net electric field is lambda z by 4 pi epsilon naught, and this integral we found just now 2L upon z square root z square plus s square. Now this z will cancel this one of the z from here, and we are getting at the last 1 upon 4 pi epsilon naught, 2 times of lambda into L, and z cancel it, so 1 z remaining here, and root z square to L square. This is the final answer of this question. And the direction of this net electric field would be along this perpendicular bisector. It has no components parallel to the rod. So students, I hope that you liked my derivation, you liked my video. So please don't forget to press the like button, and also please subscribe my channel. Thank you to all of you.